Settle in. Let the sounds around you fade. Let the edges of your awareness soften. Consider this. What if everything you see, everything humanity has ever charted in the night sky, the brilliant stars, the swirling galaxies, the luminous clouds of gas, what if all of it is merely the foam on an unseen, unfathomably deep ocean? For centuries, we have looked up, mapping the heavens. We built telescopes of increasing power, peering further and further into the cosmic expanse. We catalogued stars, measured their light, traced the elegant spirals of galaxies, watched nebulae bloom and fade like celestial flowers. We felt, perhaps, that we were beginning to grasp the scale and substance of the universe. We charted the elements, the hydrogen and helium forged in the Big Bang, the heavier elements cooked in the hearts of dying stars, the very stuff you are made of. This visible universe, the baryonic matter we understand, the atoms that form planets, suns, and ourselves, it feels substantial. It feels like everything. But the universe, it seems, holds profound secrets in the dark. In the 1930s, the sharp-eyed astronomer Fritz Zwicky was studying the Coma Cluster, a colossal gathering of galaxies. He measured how fast the individual galaxies were moving within the cluster. He calculated the total visible mass of those galaxies, the stars, the gas he could see. And he found something deeply puzzling. The galaxies were moving far too fast. Based on the visible matter, the cluster shouldn't have enough gravitational pull to hold on to these speeding members. They should have flown apart long ago. Zwicky postulated the existence of unseen matter, dunkel materia, he called it, dark matter, providing the extra gravitational glue needed to bind the cluster. His ideas, however, were largely overlooked for decades. Then, in the 1970s, astronomer Vera Rubin, alongside Kent Ford, was meticulously studying the rotation of spiral galaxies, much like our own Milky Way. She expected stars further from the galactic center to orbit more slowly, just as outer planets in our solar system orbit the Sun more slowly than inner planets, following Kepler's laws. Gravity weakens with distance, after all. But that is not what she found. Star after star, region after region, even at the very visible edges of galaxies, were orbiting at unexpectedly high, nearly constant speeds. The galaxies were spinning too fast for the amount of visible matter they contained. It was as if some vast, invisible halo of mass surrounded each galaxy, its gravitational influence dominating the galactic dynamics. Rubin's careful, undeniable observations brought the reality of dark matter firmly into the astronomical mainstream. So what is this dark matter? Decades later, we still don't know for sure. We know what it isn't. It isn't ordinary matter, protons, neutrons, electrons, that simply isn't emitting light. The abundance of light elements created in the Big Bang sets strict limits on how much ordinary or baryonic matter can exist, and it's nowhere near enough. Dark matter must be something exotic, something non-baryonic. It doesn't seem to interact with light or electromagnetic forces at all, hence, it's dark. It interacts very weakly, if at all, with ordinary matter, passing through planets, stars, and even you, mostly unnoticed. Its primary influence, the only way we know it's there, is through its gravity. Scientists hypothesize about candidate particles, perhaps weakly interacting massive particles, or WIMPs, heavy relics from the early universe, or maybe ultralight particles called axions. Vast experiments are running deep underground, shielded from cosmic rays, hoping to catch the faintest whisper of a dark matter particle bumping into a detector nucleus. Others search for signs of its annihilation or decay in cosmic rays or gamma rays from space. Yet it remains elusive, a ghostly gravitational framework upon which the visible universe is built. It forms the invisible scaffolding of the cosmic web, the vast filamentary structure along which galaxies cluster. We see its effects in the way light from distant galaxies is bent as it passes through galaxy clusters, gravitational lensing, revealing the distribution of mass, both seen and unseen. It dictates where galaxies form and how they congregate. But the darkness holds another, perhaps even stranger secret. As astronomers mapped the universe's expansion, spurred by Edwin Hubble's discovery that galaxies are moving away from us, they expected to find that this expansion was slowing down. Gravity, after all, pulls everything together. The mutual attraction of all the matter and dark matter in the universe should act as a brake. In the late 1990s, two independent teams of astronomers set out to measure this deceleration precisely. One team, led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, used type Ia supernovae, exploding white dwarf stars of remarkably consistent peak brightness, as standard candles. By measuring how faint these distant supernovae appeared, they could gauge their distance, and by measuring their redshift, they could determine how fast they were receding. The results were stunning, shocking even. The distant supernovae were fainter than expected. They were further away than they should be if the expansion was slowing down. The only explanation was that the expansion of the universe wasn't slowing at all. It was accelerating. Something was actively pushing space-time apart, overwhelming the collective gravity of all matter. This mysterious influence was dubbed dark energy. It appears to be a property of space itself, a kind of negative pressure inherent in the vacuum. Unlike matter or dark matter, which becomes diluted as the universe expands, dark energy seems to remain constant or perhaps even grow stronger as space stretches. The more space there is, the more dark energy there is, pushing expansion ever faster. Albert Einstein had once included a similar concept, the cosmological constant, in his equations of general relativity to achieve a static universe, later calling it his biggest blunder when the expansion was discovered. Now, something very much like it seems to be real and utterly dominant. So, let's tally the cosmic inventory, the ordinary matter, the atoms that make up you, me, the Earth, the Sun, all the stars and galaxies we can see. Less than 5% of the total mass energy content of the universe. Dark matter, the invisible gravitational scaffolding, around 27%, and dark energy, the enigmatic force driving cosmic acceleration, a staggering 68%. Think about that. 95% of reality is composed of substances and forces we do not understand, cannot directly perceive, yet which govern the structure, evolution, and ultimate fate of the cosmos we inhabit. Our entire experience, our whole history of observation, is limited to a tiny fraction of what truly exists. The brilliant physicist Richard Feynman offered a stark warning, relevant far beyond the laboratory. The first principle is that you must not fool yourself, and you are the easiest person to fool. Close your eyes now, if you haven't already. Feel the gentle pull of gravity holding you. Feel the presence of the room around you, the air you breathe. All seems solid, knowable, real. Yet science tells us this tangible world is merely a small component, adrift in an ocean of the unknown. We float within a universe whose fundamental nature is overwhelmingly dark, shaped by invisible matter and propelled towards an accelerating loneliness by an energy we cannot grasp. The ground beneath our cosmic feet isn't truly solid. It's influenced, governed, perhaps even ultimately determined by forces beyond our senses, beyond our current comprehension. You are governed by the invisible. Your existence unfolds within a reality dominated by darkness. It's a humbling, unsettling thought. Perfect, perhaps, for drifting slowly into the quiet mystery of sleep. We float, then, adrift in a cosmos governed overwhelmingly by the unseen, 95% hidden from our direct perception, yet orchestrating the grand cosmic ballet. But within that pervasive darkness lies perhaps the most profound, the most unsettling cosmic revelation of our time, a force working silently, relentlessly, against the familiar pull of gravity, pushing everything apart, faster and faster. What if the great story of the universe isn't destined for a fiery reunion, but for an endless, accelerating expansion into cold, dark, and utter isolation? Let that thought settle into the quiet spaces of your mind, an expansion not just continuing, but speeding up. For much of modern cosmology, the universe's fate seemed a question balanced on a knife edge. We knew from the work of astronomers like Edwin Hubble that the universe was expanding, that distant galaxies were rushing away from us. The prevailing question became, was there enough matter, enough gravitational pull, including all that unseen dark matter we now know exists, to eventually halt this outward flight? Would gravity ultimately win, pulling everything back together in a cataclysmic big crunch, a mirror image of the Big Bang? Or was the initial outward momentum too great, destined to carry galaxies further and further apart forever, perhaps slowing over infinite time, but never reversing, leading to a vastly dispersed, cold and quiet end known as the Big Freeze? It seemed a grand cosmic battle between outward momentum and inward gravity. But the universe, as it often does, held a deeper surprise. Towards the end of the 20th century, astronomers embarked on ambitious projects to measure the expansion rate precisely, hoping to determine how much it was slowing down. They used incredibly bright, distant exploding stars, type Ia supernovae, as cosmic mile markers. These supernovae have a remarkably consistent peak brightness, allowing scientists to calculate their distance by observing how faint they appear. By also measuring the redshift of their light, caused by the stretching of spacetime as they recede, astronomers could map the history of cosmic expansion. Two independent teams, working diligently, gathered data from these faint, fleeting explosions across billions of light-years. The results, when they finally emerged, were not just surprising, they were revolutionary, they were world-altering. The distant supernovae were consistently fainter than expected for a universe whose expansion was slowing down. They were further away than they should be. The only way to make sense of the data was to accept a staggering conclusion. The expansion of the universe is not slowing down. It hasn't been slowing down for the last 5 billion years or so. Instead, it is accelerating. Something is actively pushing space-time apart, overwhelming the collective gravitational pull of all the matter and dark matter combined. This mysterious influence earned the name dark energy. It doesn't seem to clump together like matter. Instead, it appears to be smoothly distributed throughout space. It acts as a sort of negative pressure, an anti-gravity inherent in the fabric of space-time itself. Its origin remains one of the most significant unsolved problems in fundamental physics. Is it related to the energy of the vacuum predicted by quantum mechanics? Perhaps. Though the theoretical value is vastly, uncomfortably larger than what we observe. Is it a new, evolving energy field permeating the cosmos? Possibly. We simply lack the answers. Albert Einstein himself once introduced a similar concept, the cosmological constant, into his equations to allow for a static universe, only to discard it later. Now, it seems something very much like his discarded idea is not only real, but is the dominant component of the cosmos, making up nearly 70% of its total energy density. Think about what this means. Billions of years ago, when the universe was smaller and denser, matter and dark matter held the upper hand. Their gravity did slow the initial expansion. But as space expanded, the density of matter decreased. Dark energy, however, seems to remain constant per unit volume of space, or perhaps even increases slightly. So, as more space was created, the total influence of dark energy grew. Eventually, about 5 billion years ago, it tipped the balance. Its repulsive force began to dominate over gravity on the larger scales, and the cosmic acceleration began. An acceleration that continues today, shaping the ultimate destiny of everything. The consequences, stretched over cosmic time, are profound. As this acceleration continues, galaxies that are not already gravitationally bound to our own local group of galaxies will recede from us faster and faster. One by one, they will cross a threshold, a cosmic event horizon. The space between us and them will be expanding so rapidly that light emitted from them will never be able to bridge the growing gulf to reach us, no matter how long we wait. It's like trying to swim upstream against a current that grows ever stronger, eventually exceeding your maximum speed. Over unimaginable timescales, the night sky will change. Distant galaxies will wink out, their light stretched beyond detection, their presence lost to us forever. Future observers, perhaps inhabiting the large elliptical galaxy formed from the eventual merger of our Milky Way and Andromeda, will look out into an increasingly empty void. The evidence of the Big Bang itself, the cosmic microwave background radiation, will be redshifted into oblivion. The very clues that allowed us to decipher cosmic history, the expansion, the distant galaxies, will vanish beyond the horizon. The universe will become islands of gravitationally bound stars adrift in an endless, accelerating dark expanse. A state of profound cosmic isolation. The writer Arthur C. Clarke once mused, two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying. Dark energy adds another layer to that thought. Even if the universe teems with life and intelligence, this accelerating expansion may ultimately isolate us, locking every galactic civilization within its own unreachable island universe. We have peered into the far future, contemplating an accelerating expansion into endless isolation, a universe fading from view. Now, let us turn our gaze in the opposite direction. Backwards, past the formation of galaxies, past the birth of the first stars, past the cooling glow of the cosmic dawn, all the way back to the very beginning, or rather, to the edge of the beginning. What happened in the moment before time itself began? What, if anything, existed before the Big Bang? Let that question sink in. Before the beginning, a concept that challenges the very structure of our thought, our language, built as it is upon sequence, upon cause and effect, unfolding within time. Our best scientific description of cosmic origins is the Big Bang model. It tells a remarkable story, supported by overwhelming evidence. The expansion of the universe discovered by Hubble, the faint afterglow of the initial fireball known as the cosmic microwave background radiation detected by Penzias and Wilson, and the precise abundances of the lightest elements like hydrogen and helium forged in the first few minutes. This model describes a universe that began approximately 13.8 billion years ago in an extraordinarily hot, incredibly dense state. It wasn't an explosion in space, like a bomb going off in a pre-existing void. It was an explosion of space itself. Space and time, matter and energy, even the laws of physics as we know them, emerged and evolved from this primordial state. We can trace this evolution back with remarkable confidence. We can model the universe fractions of a second after the beginning, when quarks and gluons swam in a hot plasma, when protons and neutrons formed, when the first atomic nuclei were synthesized. We can look back to the time the cosmic microwave background was released, about 380,000 years after the start, when the universe cooled enough for neutral atoms to form and light could finally travel freely. We can even push our understanding further back, incorporating ideas like cosmic inflation, proposed by Alan Guth and others, a hypothesized period of hyper-accelerated expansion in the very first tiny fraction of a second, smoothing out the universe and seeding the structures we see today. But even inflation, if correct, starts a minuscule moment after the absolute beginning. As we push our theories further and further back, closer and closer to time equals zero, our current physics begins to fray. Einstein's general theory of relativity, our best description of gravity and spacetime on large scales, predicts a point of infinite density and temperature at the very beginning, a singularity. At this point, the equations break down. Spacetime curvature becomes infinite. Known physics ceases to offer meaningful answers. Time itself, as described by relativity, dissolves. To understand the true origin, the moment before which our clocks cannot tick, we would need a theory that unites general relativity with quantum mechanics, a theory of quantum gravity. This is the great unfinished quest of modern theoretical physics. Ideas like string theory, suggesting fundamental reality is made of vibrating strings in higher dimensions, or loop quantum gravity, proposing that spacetime itself is quantized, made of discrete units. These are attempts to probe that ultimate frontier. But currently, they remain largely speculative, incomplete mathematical frameworks. We lack the experimental data to confirm or deny them. The earliest moment we can even begin to describe with some confidence is the Planck epoch, ending around 10 to the minus 43 seconds after the supposed beginning. Before this unimaginably small instant, quantum effects of gravity are expected to dominate, and the very concepts of space and time as smooth, continuous entities likely lose their meaning. What was there? Was there a before? Did our universe emerge from a quantum fluctuation in some larger multiverse? Is our universe part of an endless cycle of cosmic births and deaths? Was there simply nothing? And if so, how did a universe burst forth from absolute non-existence? These are questions currently beyond the reach of empirical science. The moment before time began, the instant of creation itself remains shrouded in absolute mystery. It is a boundary not just of our knowledge, but potentially of knowability itself. The physicist John Archibald Wheeler, who wrestled deeply with the mysteries of quantum mechanics and cosmology, once remarked, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance. Consider this as you drift. Your consciousness, your thoughts, your experience of time flowing forwards, all of it rests upon a foundation that is fundamentally unknown. The entire intricate, vast, comprehensible universe, operating according to elegant physical laws, emerged from a state that defies our comprehension, a point where those very laws did not yet apply. Before the ticking clock, before the expanding space, before the first particle, there is a question mark that echoes through all of existence. Feel the weight of that unknown origin. It is the ultimate mystery, the silent, absolute blankness from which everything you know, everything you are, somehow arose. Let that deep, primal unknowing cradle you, as you sink back towards the quiet mystery, from which all awareness ultimately springs. We have journeyed to the edge of time's beginning, confronting the ultimate unknown before the Big Bang. Now, let us turn our attention to objects within space-time itself that challenge our most fundamental assumptions about reality. Consider this. What if the universe forgets? What if information, the very essence of structure and history, can be utterly and irrevocably destroyed, erased from existence forever inside the darkest objects imaginable? Black holes? Allow that possibility to settle. The idea that cosmic memory might not be perfect, that erasure could be a fundamental process. In the familiar world, information seems persistent. A burned book still leaves ash and smoke containing clues about the original pages. A shattered glass still comprises the same atoms rearranged. Quantum mechanics, the bedrock of our understanding of the microworld, elevates this intuition to a rigid principle. Information is always conserved. The total information content of a closed system never decreases. It might become scrambled, incredibly difficult to decode, like the dispersed smoke from that burned book, but in principle, it's still there. The universe, according to quantum rules, remembers everything. But then, there are black holes. Predicted by Einstein's general theory of relativity, these are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. Matter and energy fall in, pulled towards a central point of theoretically infinite density, the singularity. According to relativity, anything that falls past the event horizon is lost to the outside universe forever. Its intricate details, the specific arrangement of its atoms, the quantum states of its particles, all the information it carried, seems to disappear behind that one-way membrane. As physicist John Wheeler famously quipped, black holes have no hair, meaning they are characterized only by their mass, charge, and spin. All other details, all the specific information about what formed them, seem to be smoothed away, lost. For decades, this apparent conflict between general relativity and quantum mechanics simmered. Relativity described gravity and black holes effectively isolating information, while quantum theory insisted information could not be destroyed. The tension escalated dramatically with the work of Stephen Hawking in the 1970s. Applying quantum principles near the event horizon, Hawking made a startling prediction. Black holes are not entirely black, they should slowly radiate energy, now known as Hawking radiation. This happens through complex quantum effects where pairs of virtual particles pop into existence near the horizon, one falling in and the other escaping, carrying energy away from the black hole. This discovery, while monumental, deepened the mystery. If black holes slowly radiate and evaporate over immense timescales, eventually vanishing completely, what happens to the information they swallowed? Does it escape somehow encoded within the faint Hawking radiation? Hawking initially argued no, that the radiation was thermal, random, carrying no information about the black hole's contents. This meant the information was truly finally lost when the black hole evaporated, violating the core principle of quantum mechanics. This conundrum became known as the black hole information paradox. It represents one of the most profound clashes in modern physics, pushing at the boundary where our two great theories of reality, general relativity and quantum mechanics, fail to reconcile. Physicists have grappled with it for decades. Does information somehow get imprinted on the event horizon itself, like a hologram, as suggested by the holographic principle championed by Gerard 't Hooft and Leonard Susskind? Does it leak out subtly within the Hawking radiation, requiring a deeper understanding of quantum gravity to decode? Or was Hawking initially right, and must we fundamentally revise quantum mechanics to allow for information loss? Perhaps the interior of a black hole connects to another universe, shunting the information elsewhere. Or maybe our concepts of locality and space-time break down so completely within black holes that the question itself is ill-posed. As of now, there is no consensus, no definitive answer. The paradox remains a stark reminder of the limits of our current understanding. Stephen Hawking himself, who ignited the debate, later reconsidered, suggesting information might escape, though the mechanism remains highly unclear. He once famously stated regarding the unpredictability inherent in quantum mechanics and black holes, "Not only does God play dice, but he sometimes throws them where they cannot be seen." Reflect on this unsettling possibility. We build our lives, our societies, our sense of self upon information, memories, records, identities, knowledge passed down. We strive to preserve, to remember, to leave a trace. Yet the universe might contain mechanisms for absolute erasure. What if the fundamental fabric of reality allows for perfect forgetting? If information can be lost on a cosmic scale within black holes, does that mirror the impermanence we experience in our own lives? Memories fade, data corrupts, legacies vanish. Is this fragility not just a feature of our human condition, but woven into the cosmos itself? Consider the possibility that some things, once lost, are lost completely, beyond any hope of recovery, swallowed by a darkness that doesn't just hide, but annihilates the very record of existence. Let that thought cradle you. The universe as a place not just of creation, but perhaps of ultimate, irretrievable loss. Fading slowly, like information, into the quiet void. We have considered the enigma before time itself, and the potential for absolute erasure within the hearts of black holes. Now, let us cast our gaze forward once more, far beyond the accelerating isolation of galaxies, towards the ultimate horizon, the final destiny of the cosmos itself. For everything that has a beginning, we assume an end. But what is the end for everything? Is the final chapter of the universe already determined, simply waiting to unfold? Or does the cosmos itself hang suspended, its ultimate fate still unwritten, delicately poised between unimaginable extremes, between eternal ice and unimaginable fire? Our current understanding, shaped by the discovery of dark energy and the accelerating expansion, paints a picture leaning heavily towards a cold, desolate future. This scenario, often called the Big Freeze or the Heat Death, envisions the relentless continuation of the trends we observe today. Fueled by the constant, or perhaps slowly increasing, push of dark energy, the expansion continues to accelerate. Galaxy clusters fly apart. Galaxies like our own Milky Way, bound by gravity locally, will eventually merge into larger conglomerates, but these supergalaxies will become increasingly isolated islands in an ever-expanding void. The space between them grows so vast, so quickly, that light from one island will never reach another. Cosmic horizons shrink around each galactic metropolis, locking them away from each other forever. Within these isolated islands, the cycle of starbirth will slowly wind down. The vast clouds of gas needed to form new stars will be exhausted. The stars that currently shine, like our own sun, will eventually burn through their nuclear fuel. Smaller stars, red dwarfs, will glow faintly for trillions upon trillions of years, far longer than the universe's current age, but even they will eventually fade to black dwarfs, cold, dense embers. Larger stars will have long since collapsed into neutron stars or black holes after spectacular supernova explosions. The universe will become dominated by these stellar remnants, scattered sparsely through the darkness. Over truly immense timescales, far beyond anything we can easily conceive, even these remnants may decay. Grand unified theories suggest protons themselves might be unstable, eventually decaying into lighter particles, dissolving the very substance of matter as we know it. Though the timescale for this is extraordinarily long if it happens at all. Black holes will reign for a time, slowly consuming any stray matter or radiation. But even they are not eternal. As Stephen Hawking predicted, they will slowly evaporate through Hawking radiation, shrinking over unimaginable eons until they too vanish in a final faint burst of particles. What remains? A universe almost infinitely large, almost infinitely cold, approaching absolute zero temperature. A thin, featureless soup of photons, neutrinos, electrons, positrons, and perhaps other elementary particles, drifting ever further apart in the eternal darkness. Maximum entropy will have been reached. No gradients, no structure, no potential for work or change. Just a cold, dark, empty, and endlessly expanding void. The heat death. A universe effectively dead, frozen in eternal stillness. This is the future implied by a constant dark energy, the cosmological constant. But the nature of dark energy is not definitively known. What if it is not constant? What if it is something more dynamic, something that changes with time? One possibility, explored by theoretical physicists, is known as phantom energy. In this scenario, the density of dark energy increases as the universe expands. Its repulsive force grows stronger and stronger over time, leading to a far more violent end than the slow fade of the Big Freeze. This scenario is called the Big Rip. As phantom energy grows, its outward push eventually becomes strong enough to overcome not just the gravity between distant galaxies, but all forces holding things together. First, galaxy clusters would be torn apart. Then, the gravity-binding individual galaxies like our own would be overwhelmed, scattering stars into the void. Soon after, the gravitational pull holding solar systems together would fail. Planets flung away from their dying stars. As the end approaches rapidly, the electromagnetic forces holding atoms and molecules together would yield, disintegrating planets, stars, and even you into unbound atoms. Finally, in the last fractions of a second, the phantom energy would become so strong it would overcome the strong nuclear force holding atomic nuclei together, ripping protons and neutrons apart. And ultimately, space-time itself would be torn asunder. The fabric of reality unraveled, an end not of cold stillness, but of infinite, violent expansion, tearing everything, down to the most fundamental level, into nothingness. Imagine that. Reality itself coming undone at the seams, ripped apart by an accelerating darkness. These two fates, the infinite cold of the Big Freeze or the violent tearing of the Big Rip, seem the most plausible based on current observations of accelerating expansion. But they are not the only possibilities, because our understanding remains incomplete. What if dark energy is not permanent? What if it were to decay, or even reverse its sign in the distant future, becoming attractive instead of repulsive? If that happened, gravity, relentless and patient, could regain the upper hand. The accelerating expansion would slow, halt, and then reverse. The universe would begin to contract. Galaxies, initially flying apart, would start rushing towards each other. The cosmic microwave background radiation, the faint afterglow of the Big Bang, would begin to heat up again as space compressed, eventually becoming hotter than the surfaces of stars. The universe would grow smaller, denser, hotter. Stars and galaxies would collide and merge. Black holes would coalesce. Eventually, everything would collapse back towards an infinitely hot, infinitely dense state. A big crunch. A fiery Götterdämmerung, potentially mirroring the conditions of the Big Bang itself. Could this big crunch then lead to another Big Bang? Some cyclical models of the universe, like the ekparodic scenario proposed by Paul Steinhardt and Neil Turok, envision such bounces, endless cycles of expansion and contraction, fire giving way to cooling only to collapse back into fire once more. Our universe could be just one iteration in an eternal cosmic dance of creation and destruction. And there are even more exotic possibilities lurking in the unexplored territory of fundamental physics. What if the vacuum of space-time itself is not truly stable? Some theories suggest our universe exists in a false vacuum state, a seemingly stable energy level, but not the lowest possible one. It's possible that, through a random quantum fluctuation, a bubble of true vacuum could appear somewhere in the universe. This bubble would expand at nearly the speed of light, converting the false vacuum to the true vacuum as it goes. Inside this bubble, the fundamental constants of nature, the laws of physics as we know them, could be radically different. Our current form of existence would be impossible. Such a vacuum decay event would rewrite reality itself, instantly and irrevocably. A sudden, fundamental transformation of everything. So, the ultimate fate remains uncertain, balanced on the knife edge of our ignorance about the true nature of dark energy and the fundamental laws governing reality at its extremes. Will it be the endless cold dark of the Big Freeze, the violent tearing of the Big Rip, a fiery return in the Big Crunch, perhaps leading to rebirth, or a sudden, universe-altering phase transition? We simply do not know. The final act of the cosmic drama is yet to be written. The physicist Steven Weinberg, contemplating the vastness and seeming indifference of the cosmos, observed, "The more the universe seems comprehensible, the more it also seems pointless." Consider this vast uncertainty as you drift towards sleep. We live our brief lives, experience our personal endings, plan for our futures, all while unfolding within a universe whose own ultimate destiny hangs in profound question. It is a future that could unfold over unimaginable trillions of years of slow fading, or end in a sudden, violent convulsion, or perhaps return to the fire of its birth. We are actors in a play whose final scene is unknown, potentially unwritten, poised between ultimate cold, ultimate heat, ultimate disintegration, or ultimate transformation. Feel yourself floating within this immense cosmic uncertainty. Your existence is a fleeting moment against a backdrop of potential eternities, each profoundly different, each determined by forces beyond our current grasp. There is no cosmic guarantee, no final answer yet revealed, only the vast, silent, patient unfolding of space-time, carrying us all towards an unknown end. Let that profound ambiguity hold you as you release into the quiet, deep mystery. You feel the world around you, the pressure where you rest, the quiet sounds in the room. It seems solid, reliable, predictable. But what if this tangible reality, this sturdy stage upon which your life unfolds, is merely a surface? What if, just beneath the familiar appearance of things, lies a realm of profound strangeness, a foundation of reality that defies all common sense? What if the very building blocks of your existence operate according to rules that are deeply, unsettlingly weird? This is the world described by quantum mechanics. Developed in the early 20th century by pioneers like Max Planck, Niels Bohr, Erwin Schrödinger, and Werner Heisenberg, it is the physics of the very small, of atoms, electrons, photons. It is arguably the most successful scientific theory ever conceived, underpinning everything from lasers and computers to our understanding of chemical bonds and nuclear reactions. Yet, its core principles paint a picture of reality utterly alien to our everyday intuition. Consider superposition. In our world, an object is here, or it is there. A switch is on, or it is off. But in the quantum realm, a particle like an electron can exist in a combination of multiple states at the same time. It can be spinning clockwise and counterclockwise simultaneously. It can be in multiple locations at once, described only by probabilities, a wave of potentiality spread across space. Only when we attempt to measure it, to force it to reveal itself, does this wave of possibilities collapse into a single definite state. It's as if reality holds its breath, existing in a ghostly blend of potentialities until observed. The famous thought experiment of Schrödinger's cat, simultaneously alive and dead until the box is opened, was designed to highlight the sheer absurdity of applying these rules to our macroscopic world. Yet these rules govern the foundation upon which our world is built. Then there is entanglement. Imagine two particles, born from the same event, linked in some profound way. They fly apart, perhaps across vast cosmic distances. According to quantum mechanics, they remain connected. If you measure a property of one particle, say, its spin, you instantly influence the corresponding property of the other particle, no matter how far away it is. Instantly, faster than light could travel between them. Albert Einstein famously called this spooky action at a distance, deeply skeptical of its implications. It suggests a hidden layer of reality, an interconnectedness that defies our notions of locality and separation. Things can be linked in ways that transcend space, bound by an invisible quantum thread. And consider quantum tunneling. Imagine throwing a ball at a solid wall. It bounces back, it doesn't have enough energy to pass through. But quantum particles face barriers differently. There is always a small but non-zero probability that a particle can simply appear on the other side of a barrier it seemingly lacks the energy to overcome. It tunnels through reality's obstacles. This ghostly ability is not just a theoretical curiosity, it is essential for life itself. The fusion reactions powering our sun rely on protons tunneling through their mutual electrical repulsion to get close enough to fuse. The transistors in the device you might be listening on operate thanks to electrons tunneling across tiny gaps. The seemingly solid world is, at its quantum roots, porous, permeable to these strange leaps. Wave-particle duality further confounds our classical picture. Sometimes particles like electrons or photons behave like localized point-like objects, particles. Other times, they behave like spread-out waves, interfering with each other like ripples on a pond. How they behave depends entirely on how you design the experiment to observe them. The very act of observation seems to influence the nature of the reality being observed. Is it a wave or is it a particle? The quantum answer seems to be it's both and neither until you look. These concepts, superposition, entanglement, tunneling, duality, are not mere speculation. They are experimentally verified facts about the fundamental nature of reality. The universe, at its deepest level, does not operate like the clockwork machine envisioned by classical physics. It is a realm of probabilities, uncertainties, interconnectedness, and observer-dependent phenomena. Niels Bohr, one of the founding fathers of this strange science, captured the essence of this departure from classical reality when he said, "Everything we call real is made of things that cannot be regarded as real." Let that sink in. Everything you perceive as solid, definite, and separate, your body, the ground beneath you, the stars above, is composed of these quantum entities behaving in these counterintuitive ways. Your own atoms flicker in and out of existence in a probabilistic dance. Particles within you might be entangled with particles elsewhere in the cosmos. The solidity you feel is perhaps an illusion, an emergent property arising from the statistical behavior of countless trillions of these fundamentally uncertain components. The clear boundaries we perceive may dissolve at the quantum level into a fuzzy, interconnected haze. As you lie here, letting go, perhaps the feeling of boundaries softening, of thoughts drifting, of the solid world becoming less defined as sleep approaches. Perhaps this mirrors, in some small way, the underlying quantum nature of reality itself. Beneath the surface of certainty lies a deep, unsettling, probabilistic strangeness, a world less like solid rock and more like a shimmering, uncertain fog. Embrace that strangeness. It is the foundation of your existence, the unsettling truth that reality is far more ghostly, interconnected, and mysterious than it appears. A perfect thought, to dissolve into, as you drift, into the quantum foam of sleep. We have explored the strangeness lurking beneath familiar reality, the quantum fuzziness that underpins the solid world. Now consider another profound mystery, one hiding in plain sight within the very equations scientists use to describe the cosmos. Why does mathematics, a language seemingly born from human logic and abstraction, work so incredibly well to describe the physical universe? Why is reality, from the smallest particle to the largest galaxy cluster, so unreasonably amenable to mathematical description? Look around the history of science. Isaac Newton described the motion of planets and falling apples with elegant differential equations. James Clerk. Maxwell captured the entirety of classical electricity, magnetism, and light in a handful of beautiful vector calculus equations. Albert Einstein revealed the curvature of spacetime through the complex tensor fields of general relativity, predicting phenomena like gravitational lensing and black holes decades before they were observed. Erwin Schrödinger and Werner Heisenberg laid the foundations of quantum mechanics using abstract mathematical structures like wave functions and matrices, describing a subatomic world utterly alien to our senses, yet perfectly predicted by the math. The predictive power born from these equations is astonishing. They don't just describe what we see, they predict phenomena we haven't yet observed. Maxwell's equations predicted radio waves. Dirac's quantum equations predicted the existence of antimatter. The mathematics told us where to look for Neptune. It seems the universe plays by strict mathematical rules, rules we can uncover through observation, logic, and calculation. But where does mathematics itself come from? Is it an invention of the human mind, a tool we created to organize our thoughts and quantify the world? Or is it a discovery, an eternal, pre-existing structure of logical relationships that we stumble upon, like explorers finding a hidden continent? Numbers, shapes, theorems about prime numbers or the nature of infinity. These seem to exist in a purely abstract realm, independent of physical reality. Yet, time and again, abstract mathematical concepts developed purely for their own intellectual beauty, sometimes centuries earlier, find unexpected and powerful applications in describing the physical world. Non-Euclidean geometry, once a mathematical curiosity, became the language of Einstein's gravity. Group theory, developed to study symmetries, became essential in particle physics. The physicist Eugene Wigner wrote a famous essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," marveling at this very mystery. He called it a miracle and a wonderful gift which we neither understand nor deserve. Why should the universe obey laws expressible in the language of human-discovered abstract mathematics? Is it a coincidence? Is it that our minds are tuned to find mathematical patterns, imposing them on reality? Or does it suggest something deeper about the nature of the cosmos itself? That perhaps, at its most fundamental level, the universe is mathematical. Galileo Galilei famously declared, "Philosophy, nature, is written in that great book which ever lies before our eyes, I mean the universe, but we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. This book is written in the mathematical language." Consider this profound alignment, the intricate dance of atoms, the vast architecture of galaxies, the very flow of time and expansion of space, all seem to follow precise mathematical scripts. It's as if reality is built upon an underlying code, an operating system written in the language of numbers and equations. We, as conscious beings capable of understanding some of this mathematics, are in a unique position to read fragments of this cosmic code. But the mystery remains deeply unsettling. Why this mathematics? Why these specific constants, these particular symmetries? Does this mathematical underpinning imply a kind of preordained logic, a structure that exists independently of physical matter? Does it hint at a reality far more abstract and less tangible than our senses perceive? Perhaps our messy, complex emotional lives, our perceptions of color, sound, and feeling are emergent phenomena arising from this starkly elegant, perhaps coldly logical, mathematical substrate. As you lie here, letting your thoughts drift, feel the subtle order that underlies the apparent chaos of the world, the regular rhythm of your breath, the predictable cycle of day and night, the very structure of the matter that makes up your body, all governed by laws expressible through mathematics. Yet the connection feels distant, almost unbelievable. Why should your existence, your consciousness, be rooted in something as abstract as number theory or differential geometry? It's a profound disconnect between the lived experience and the underlying description. The universe speaks in equations, a language we are only beginning to decipher. A language whose very existence as the bedrock of reality is a deep and perhaps unsolvable mystery. Allow yourself to float in that wonder, the quiet hum of the cosmos, perhaps the sound of mathematics itself, whispering the rules of existence as you drift, slowly, into sleep. We've pondered the uncanny effectiveness of mathematics in describing reality. Now, let's focus on the results of those mathematical laws, specifically as they pertain to our own existence. Consider the universe we inhabit. It seems exquisitely tuned, possessing just the right properties, just the right physical constants, to allow for the emergence of complexity, structure, stars, planets, chemistry, and ultimately, life. Why are the fundamental parameters of the cosmos seemingly so perfectly arranged for our existence? Are these cosmic coincidences just incredibly lucky accidents, or do they hint at something more profound, something deeply unsettling, about our place in the vastness? Think about the fundamental forces governing reality. Gravity pulls matter together, strong enough to form stars and galaxies, yet weak enough that stars don't collapse instantly. The electromagnetic force holds atoms together, governing chemistry, yet its strength relative to gravity is precisely balanced to allow stars to ignite and sustain fusion over billions of years. The strong nuclear force binds protons and neutrons in atomic nuclei, but if it were just slightly stronger, all hydrogen would have fused into heavier elements in the Big Bang, leaving no fuel for long-lived stars like our Sun. If it were slightly weaker, complex nuclei couldn't form at all. The weak nuclear force governs radioactive decay and plays a crucial role in supernova explosions that distribute heavy elements needed for life, elements forged in stellar cores. Its strength, too, appears finely tuned. Consider the masses of fundamental particles. The neutron is slightly heavier than the proton. This allows free neutrons to decay into protons, but keeps protons stable. If the proton was slightly heavier, it would decay, and atoms as we know them could not exist. The mass of the electron relative to the proton influences the size of atoms and the nature of chemical bonds. Think about the properties of space-time itself. We live in a universe with 3 large spatial dimensions. Why not 2, or 4, or 10? Calculations suggest that stable planetary orbits and complex atomic structures might be impossible or vastly different in universes with a different number of dimensions. Consider the amount of dark energy. Its measured value is incredibly small compared to theoretical predictions from quantum physics, smaller by a staggering 120 orders of magnitude. If dark energy were significantly larger, its repulsive force would have overwhelmed gravity from the beginning, preventing galaxies and stars from ever forming. If it was significantly negative, the universe would have rapidly collapsed back on itself. Its tiny positive value allows for structure formation early on, followed by the gentle acceleration we now observe. There's also the balance between matter and antimatter. In the very early universe, they should have been created in almost equal amounts. Yet somehow, a tiny asymmetry allowed for slightly more matter to survive the mutual annihilation, leaving behind the substance that makes up everything we see today. If the balance had been perfect, the universe would be filled only with radiation, devoid of matter. These are just a few examples of what is sometimes called the fine-tuning problem. Numerous fundamental constants and initial conditions of the universe appear to fall within exceedingly narrow ranges that are necessary for the existence of complex structures and life as we know it. Change any of them, even slightly, and the resulting universe would be drastically different, perhaps sterile, empty, or fleeting. So, why this apparent fine-tuning? Several explanations have been proposed, each with profound implications. Perhaps it is simply a brute fact, an astonishing coincidence. We just happen to live in a universe where the dice rolled perfectly. Given infinite possibilities, perhaps one incredibly lucky outcome was bound to occur, and since we are here to observe it, we naturally find ourselves in such a universe. This is related to the anthropic principle, which, in its weak form, states that our observations of the universe must be compatible with the existence of conscious observers. We see the universe as fine-tuned for life, because if it weren't, we wouldn't be here to see it at all. Another possibility invokes the multiverse. Perhaps our universe is just one among a vast, maybe infinite, ensemble of universes, each with different physical constants and laws. In most of these universes, conditions are hostile to life. But inevitably, within this cosmic landscape, some universes, like ours, will possess the right properties by chance. We naturally find ourselves in one of the habitable ones. This elegantly explains the fine-tuning, but postulates an immense unobservable reality beyond our own. Or perhaps there is some deeper underlying physical principle we haven't yet discovered, A theory of everything that dictates these constants must have the values they do, showing that the tuning isn't arbitrary but necessary. However, we currently have no such confirmed theory. Finally, some might see fine-tuning as evidence for deliberate design, though this steps outside the realm of conventional scientific explanation. The astrophysicist Sir Martin Rees, who has written extensively on fine-tuning, stated, "Our universe could be just one element, one atom, as it were, in an infinite ensemble, a cosmic archipelago. The seemingly designed features of our universe may then not be uniquely ordained by the underlying unified theory, but represent environmental accidents. Reflect on this delicate balance. Your existence, the existence of Earth, the stars you see, the very possibility of complexity and thought, all seem contingent on a remarkable series of cosmic coincidences. The fundamental parameters of reality appear dialed in with breathtaking precision. Are you the beneficiary of an almost unbelievable stroke of luck in a single universe? Or is your existence evidence of a far grander, perhaps infinite, cosmic landscape where all possibilities are realized? Or does it point towards a deeper, yet unknown, physical necessity? Whichever explanation resonates, it underscores the precariousness, the sheer improbability of a universe capable of producing beings who can ponder these very questions. Feel the weight of these cosmic parameters holding steady, allowing the intricate dance of chemistry and life to unfold. You are here because the universe is just right. And the reason why remains one of the deepest, most unsettling questions we can ask. Let that cosmic coincidence, that delicate balance, cradle you, as you drift, into the improbable quiet of sleep. We have contemplated the seemingly miraculous fine-tuning of the cosmos that allows for complexity and life. But perhaps the greatest miracle, the deepest enigma arising from that complexity, resides not in the distant stars or fundamental constants, but right here, within you. How does the simple, lifeless matter, governed by the laws of physics and chemistry, the carbon, hydrogen, oxygen, nitrogen atoms, forged in stars and assembled according to mathematical rules, give rise to the subjective, qualitative richness of your inner world? How does the wet electrochemical activity of your brain generate the feeling of being you? The emergence of consciousness from seemingly non-conscious matter remains one of the most profound and perhaps fundamentally intractable mysteries in all of science. Think about what consciousness entails. It's the redness of red, the warmth of sunlight on your skin, the bitterness of coffee, the melody of music, the sting of sadness, the joy of connection, the flow of thoughts, the very sense of self, of being an I experiencing the world. These subjective qualities, often called qualia, are the defining characteristic of conscious experience. Neuroscience has made incredible strides in mapping the brain and correlating neural activity with conscious states. We can see which brain regions light up when you recognize a face, feel fear, or make a decision. We understand the intricate dance of neurons firing, neurotransmitters crossing synapses, electrical signals propagating through complex networks. We can even manipulate brain activity to alter perception or mood. Technologies like fMRI and EEG give us unprecedented windows into the working brain. We are uncovering the correlates of consciousness, the physical processes associated with subjective experience. But correlation is not explanation. Knowing which physical processes accompany consciousness doesn't tell us why or how those processes generated. Why should a specific pattern of electrochemical signals firing between billions of neurons feel like anything at all from the inside? Why isn't it all just complex information processing happening in the dark, like a sophisticated computer executing its program without any inner awareness? This is often referred to as the hard problem of consciousness, a term coined by the philosopher David Chalmers. The easy problems, relatively speaking, involve understanding the brain's functions, how it processes information, controls behavior, integrates sensory input. The hard problem is explaining subjective experience itself. How does mere matter, arranged in a particular complex pattern, suddenly light up with awareness? What is the physical mechanism that bridges the gap between objective neuronal activity and subjective feeling? Is consciousness an emergent property, arising naturally from sufficient complexity, like wetness emerging from the interaction of water molecules? If so, what is the threshold of complexity required? Could advanced artificial intelligence become conscious? Or is consciousness something more fundamental, perhaps woven into the fabric of reality itself, as some panpsychist theories suggest, the idea that consciousness, in some rudimentary form, might be a property of all matter? Could quantum mechanics play a role, as suggested by theorists like Roger Penrose and Stuart Hameroff? Perhaps the delicate quantum states within microtubules inside neurons allow for a form of computation linked to conscious awareness, bridging the gap between the quantum world and subjective experience. These ideas remain highly speculative and controversial within the scientific community. Or is consciousness simply an illusion, a useful fiction generated by our brains to help us navigate the world, as argued by philosophers like Daniel Dennett? Perhaps the feeling of a unified self experiencing qualia is a kind of sophisticated user interface, hiding the complex, non-conscious computations happening underneath. Despite centuries of philosophical debate and decades of focused scientific research, we seem no closer to a definitive answer. Consciousness remains stubbornly resistant to explanation within our current scientific framework. It challenges the purely materialistic, reductionist view that everything can ultimately be explained by the interactions of mindless physical components. It sits at the intersection of physics, biology, psychology, and philosophy, a mystery that touches the very core of what it means to be human, to exist, to experience. The physician and writer, Oliver Sacks, who explored the mysteries of the mind through his patients' experiences, reflected, "There will be no complete science of life. No single theory comprehending the levels of protein, cell, tissue, organ, organism, and biosphere, without a profound understanding of the interactions and dynamics of these levels, how they give rise one to the other. A science of emergence." And central to this will be the emergence of mind, of consciousness, which seems to arise from a critical mass or density of neuronal complexity and interaction. Yet, how it arises remains the question. Consider your own awareness right now. This intimate, undeniable, yet utterly inexplicable fact of your subjective experience. It arises from the mundane stuff of the universe, atoms identical to those in stars and rocks, organized in the intricate structure of your brain. Yet, it feels like something entirely different, something immaterial, something personal. This inner light, this feeling of being, is the ultimate mystery staring back at you from the mirror. Science can describe the brain that produces it, but the leap from physical processes to subjective feeling remains a vast, dark chasm in our understanding. You are a conscious island in a universe that, as far as we know, is largely unconscious. How did this island arise? Why does it feel the way it does? As you drift towards sleep, feel the texture of your own consciousness, the dimming light, the fading sounds, the shifting thoughts. This very experience is the deepest enigma. Let yourself float within it, the unexplained miracle of awareness itself, fading gently into the quiet mystery from which it arose. We have explored the mystery of consciousness emerging from lifeless matter. Now, let us delve into a related, perhaps even more unsettling question that strikes at the heart of our sense of self and agency. Do you truly choose your thoughts, your actions, your path in life? Or is the feeling of free will, the sensation of being the conscious author of your decisions, merely an illusion generated by a brain operating according to deterministic physical laws? Are you truly free, or are you simply experiencing the unfolding of a predetermined script? This question has been debated by philosophers for millennia, but modern science, particularly neuroscience and physics, adds compelling and often uncomfortable layers to the discussion. Consider the physical world. From the predictable orbits of planets described by Newton's laws to the chemical reactions governed by quantum mechanics, the universe seems to operate according to fixed rules. Given the initial conditions of a system and the laws governing it, its future state appears in principle entirely determined. Cause follows effect in an unbroken chain stretching back to the Big Bang. Your brain, the organ from which your thoughts and decisions arise, is a physical system. It is composed of atoms and molecules obeying the same laws of physics and chemistry as everything else. Neurons fire based on electrochemical gradients, neurotransmitters bind to receptors according to molecular shapes, signals propagate along established pathways. While the sheer complexity is staggering, billions of neurons, trillions of connections, it remains a physical system governed by physical law. If the state of your brain at one moment is determined by its state the moment before, tracing back through an unbroken chain of causation, where is the room for a non-physical you to step in and freely alter the outcome? Neuroscience experiments have added fuel to this deterministic view. Studies pioneered by Benjamin Libet in the 1980s and refined since have used EEG to monitor brain activity while subjects make simple decisions, like when to flick their wrist. Libet found that detectable brain activity signaling the impending action, the readiness potential, began before the subjects reported consciously deciding to move. It was as if the brain had already initiated the action unconsciously, and the conscious feeling of having decided came slightly later, perhaps as a rationalization or an observation of what the brain was already doing. While the interpretation of these experiments is debated, they raise profound questions about whether our conscious intention truly causes our actions or merely follows them. If decisions are initiated unconsciously based on prior brain states, which were determined by even earlier states, tracing all the way back to factors outside your control, your genes, your upbringing, the environment, random quantum fluctuations, then the feeling of being in conscious control might be a post hoc construction. A compelling story the brain tells itself about why it did what it did. But what about the uncertainty inherent in quantum mechanics? Doesn't the probabilistic nature of the quantum world introduce randomness, breaking the chain of strict determinism? Perhaps. Quantum events might introduce genuine unpredictability into brain processes. However, randomness is not the same as freedom. If your actions are partly determined by random quantum fluctuations in your neurons, that doesn't seem to grant you conscious control either. It simply means your actions are partly determined by prior causes and partly by chance, rather than being freely chosen by a conscious self. Replacing strict determinism with probabilistic determinism doesn't necessarily rescue the intuitive notion of free will. The implications are deeply unsettling. If free will is an illusion, what does that mean for responsibility, morality, praise, and blame? If a person's actions are the inevitable outcome of their brain state and history, can they truly be held responsible in the way we normally assume? It challenges our legal systems, our social structures, and our most intimate sense of self. Who are you, if not the conscious chooser of your actions? Some philosophers and scientists, known as compatibilists, argue that free will can coexist with determinism. They redefine free will not as the ability to have done otherwise in the exact same circumstances, which determinism seems to preclude, but perhaps as acting according to your conscious desires and values without external coercion, even if those desires and values were themselves determined by prior causes. You are free in the sense that your actions flow from your internal state, even if that internal state is ultimately determined. Others maintain that this compatibilist freedom isn't the genuine article, that the intuitive feeling of being able to choose differently, of being the ultimate originator of your actions, is incompatible with a deterministic universe governed by physical law. They might be hard determinists, accepting that free will is an illusion, or libertarians, holding on to the belief in genuine free will, perhaps by positing that consciousness somehow operates outside the known laws of physics, or that our understanding of physics is incomplete. The physicist Albert Einstein, reflecting on determinism, expressed a view that aligns with the loss of traditional free will. Everything is determined, the beginning as well as the end, by forces over which we have no control. It is determined for the insect as well as for the star. Human beings, vegetables, or cosmic dust, we all dance to a mysterious tune, intoned in the distance by an invisible piper. Consider your own choices, big and small. The decision to listen to this, the path your life has taken, the thoughts arising in your mind right now. Do they feel freely chosen? Or can you trace them back, step by step, to influences, experiences, biological predispositions? The feeling of freedom is powerful, perhaps even essential for navigating the world. Yet, the scientific picture suggests this feeling might be a sophisticated illusion conjured by the intricate, deterministic, or perhaps probabilistic, machinery of your brain. You might be like a complex wave moving through the ocean, experiencing the ride, feeling the crests and troughs, but ultimately guided by the currents and forces that shaped you, forces stretching back to the beginning of time. As you relax, let go of the feeling of control. Allow thoughts and sensations to arise and pass without judgment, without the need to claim authorship. Perhaps embracing this potential lack of ultimate control, this possibility of being part of a grand, unfolding cosmic process, is itself a kind of freedom. A release into the flow, letting the mysterious tune guide you, gently, into sleep. Consider the intricate machinery of your own body, the rhythmic beat of your heart, the steady inhale and exhale of your breath, the complex cascade of signals firing within your brain. Science tells us this is all chemistry. Exquisitely complex, self-regulating, information-processing chemistry, but chemistry nonetheless. Life, in its essence, appears to be an accidental, emergent property of non-living matter under specific conditions. Yet, you experience it. From this intricate dance of molecules arises the undeniable reality of your awareness, your feelings, your consciousness. How can a mere accident of chemistry feel like this? Think back to the early Earth, billions of years ago. A sterile rock, bombarded by radiation, surrounded by a noxious atmosphere of simple gases, methane, ammonia, water vapor, hydrogen sulfide. Oceans formed, heated by volcanic activity, energized by lightning strikes and ultraviolet sunlight. Within this primordial soup, simple inorganic molecules reacted, driven by available energy, forming slightly more complex organic molecules. In the 1950s, the famous Miller-Urey experiment simulated these conditions, zapping simple gases with electrical sparks. They found, remarkably, that amino acids, the building blocks of proteins, essential components of life as we know it, formed spontaneously. From these simple building blocks, the path to life remains shrouded in deep mystery, but the outlines are forming. Somehow, over vast stretches of time, these organic molecules became more concentrated, perhaps in tidal pools, near deep-sea hydrothermal vents, or bound to the surfaces of clay minerals. They began to link together, forming longer chains, polymers. Perhaps RNA molecules, capable of both storing genetic information like DNA and catalyzing chemical reactions like proteins, played a crucial early role, leading to the hypothesis of an RNA world preceding modern DNA-based life. The next crucial step was encapsulation. Lipid molecules, which naturally form spherical membranes in water, could have enclosed collections of these self-replicating molecules and other supportive chemicals, creating the first primitive cells, or protocells. These membranes provided a contained environment, concentrating reactants and separating the internal chemistry from the chaotic outside world. Within these tiny chemical bags, systems of metabolism could evolve. Networks of reactions allowing the protocell to harness energy and resources from its environment to maintain itself and reproduce. Natural selection would then begin its slow, patient work. Protocells that were slightly more stable, slightly better at replicating, slightly more efficient at acquiring resources, would leave more descendants. Through endless cycles of replication with variation and selection, driven purely by the laws of chemistry and physics interacting with the environment, life grew more complex, diversified, evolved, the intricate cellular machinery we see today. There was no plan, no guiding hand, no inherent drive towards consciousness or complexity. It appears to be a story of chemical contingency, of reactions happening because they could, of structures persisting because they were stable, of replication succeeding because it was efficient. An accident, a profoundly intricate, beautiful, but ultimately accidental outcome of planetary chemistry. The biologist Jacques Monod powerfully expressed this view. The universe was not pregnant with life, nor the biosphere with man. Our number came up in the Monte Carlo game. Is it any wonder if, like the person who has just made $1 million at the casino, we feel strange and slightly unreal? Feel that strangeness now. You are the result of that winning number in the cosmic casino. A complex cascade of chemical reactions initiated billions of years ago in some warm little pond or volcanic vent has culminated, through an unbroken chain of replication and evolution, in the conscious being lying here, listening. Objectively, you are an arrangement of molecules, processing energy, exchanging matter with your environment. Your thoughts are electrochemical signals, your feelings are hormonal fluctuations and neural firing patterns. Your sense of self is a construct of complex feedback loops within your brain, all chemistry, all physics, all potentially accidental. And yet, the experience, the undeniable feeling of being alive, the warmth of comfort, the coolness of the air, the memory of sunlight, the echo of laughter, the burden of sorrow, the simple awareness of existing right now. Where does this subjective richness come from? How does the mechanical execution of chemical processes translate into the vibrant, qualitative feel of existence? Science describes the mechanism, the how of the chemical processes with increasing detail. But the why of the experience arising from that mechanism remains elusive. Why does this particular complex chemical reaction feel like anything at all? It is the ultimate paradox. You are stardust, animated by accidental chemistry, a fleeting, complex pattern in the material universe, but you are also the universe experiencing itself, subjectively, from the inside. This awareness, this feeling, born from mindless molecules interacting according to blind laws, is perhaps the most astonishing phenomenon in the cosmos. It wasn't intended, it wasn't necessary, and yet, here you are, experiencing, feeling, being. Let the wonder and the unsettling nature of this truth wash over you. You are an accident, and you are a miracle, a chemical machine that feels. A brief spark of awareness ignited by chance in the vast, indifferent darkness. Embrace the sheer improbability, the strange gift, of experiencing the universe through this fragile vessel of accidental chemistry, as you drift, softly, into sleep. Consider this very moment, the feeling of stillness, the sounds reaching your ears, the thoughts drifting through your mind. It feels definite, real, present. But what if this solidity, this sense of a single unfolding reality, is merely the surface manifestation of a deeper, constantly shifting sea of possibilities? What if every single instant, at its most fundamental level, is not a certainty, but a complex tapestry woven from quantum probabilities? Classical physics painted a picture of a clockwork universe. If you knew the precise position and momentum of every particle, you could, in principle, predict the future with absolute certainty. The present was a fixed point, the inevitable consequence of the past and the guaranteed precursor of the future. But quantum mechanics, the physics of the very small, shattered this deterministic dream. It revealed a universe built not on solid certainties, but on shifting probabilities and inherent uncertainties. At the heart of quantum mechanics lies the wave function, an abstract mathematical description pioneered by Erwin Schrödinger. The wave function doesn't tell you where a particle is. It tells you the probability of finding the particle at any given location if you were to look for it. Before observation, the particle doesn't have a definite position. It exists as a wave of potentiality spread out across space, encompassing all possible outcomes according to their likelihood. This is the principle of superposition. The particle exists in a probabilistic blend of all its possible states simultaneously. Think of an electron orbiting an atomic nucleus. We often picture it like a tiny planet orbiting a star, following a definite path, but the quantum picture is far stranger. The electron exists as a cloud of probability density around the nucleus, a region where it is likely to be found, but without a precise location or trajectory until measured. Its existence is fundamentally probabilistic, described by the wave function. What happens when we try to measure the particle, to pinpoint its location or momentum? The act of measurement, the interaction with a macroscopic apparatus or observer, seems to force the universe to make a choice. The wave function instantaneously collapses. The cloud of probabilities vanishes, and the particle materializes in one specific location with one definite property. Which outcome occurs is fundamentally random, governed only by the probabilities encoded in the wave function before the collapse. It's as if reality throws dice at the quantum level every time an interaction occurs that qualifies as a measurement, a deeply mysterious process itself known as the measurement problem. Werner Heisenberg's famous uncertainty principle formalizes this inherent fuzziness. It states that you cannot simultaneously know certain pairs of properties of a particle, like its exact position and exact momentum, with perfect accuracy. The more precisely you measure one, the less precisely you can know the other. There is a fundamental limit to the certainty we can extract from the quantum world. It's not just a limitation of our measuring devices, it seems to be an intrinsic feature of reality itself. Uncertainty is woven into the very fabric of existence. Now, extend this principle beyond single particles. Everything around you, including your own body, is composed of these quantum particles, electrons, protons, neutrons, governed by wave functions and probabilities. If the fundamental constituents exist in a state of potentiality until observed or interacting, what does that imply about the macroscopic world they build? It suggests that the seemingly solid, definite reality we perceive is constantly emerging from this underlying quantum foam of probabilities. Every interaction, every moment, represents a continuous cascade of wave function collapses, selecting one outcome from countless possibilities. The chair you might be sitting on, the air you breathe, the neurons firing in your brain. All are vast collections of quantum systems constantly resolving their inherent uncertainties through interactions. The present moment isn't a single predetermined point on a timeline, but rather the specific realized outcome of an incredibly complex quantum probability calculation unfolding across the universe. The future is not merely unknown, it is genuinely undecided at the most fundamental level, a branching tree of possibilities described by evolving wave functions. Richard Feynman, known for his deep insights into quantum mechanics, offered a perspective on this probabilistic nature. The theory of quantum electrodynamics describes nature as absurd from the point of view of common sense, and it agrees fully with experiment, so I hope you can accept nature as she is. Absurd. Contemplate the implications. The reality you experience, this specific sequence of moments, is just one path taken through an infinite garden of forking quantum paths. Countless other potential realities, described by different outcomes of quantum measurements, flicker just beyond the veil of actuality, consistent with the same underlying laws but unrealized in our specific history. Every single moment you experience is a delicate crystallization, a specific pattern pulled from the vast ocean of quantum potential. The feeling of solidity, of certainty, is perhaps a high-level approximation, masking the fundamentally probabilistic, uncertain, and constantly fluctuating nature of existence at its deepest level. Your present is a fragile island built moment by moment from the shifting waves of quantum chance. We have touched upon the probabilistic nature of existence, the idea that reality crystallizes moment by moment from a sea of quantum potential. Let us now dive deeper into this strange foundation. Consider the possibility that the world you perceive, the world of solid objects, distinct locations, and predictable interactions, is merely a thin veneer, a classical approximation overlaying a reality that is far more fundamentally quantum, far more interconnected and bizarre than your senses or intuition could ever grasp. What if the apparent solidity is the illusion and the underlying quantum weirdness is the true nature of things? Quantum mechanics, as we've seen, describes the microscopic world with uncanny accuracy. But we tend to think of its strangest effects, superposition, entanglement, tunneling, as being confined to that realm, somehow washing out or becoming irrelevant at the scale of everyday objects. We experience a cat as either alive or dead, not both. We see a ball bounce off a wall, not tunnel through it. We perceive objects as having definite locations, not existing as probability waves. This transition from the quantum description at small scales to the classical description we experience at large scales is one of the deepest mysteries, often related to the concept of decoherence. Decoherence suggests that interactions with the surrounding environment rapidly destroy the delicate quantum superpositions of macroscopic objects, effectively forcing them into definite classical states very quickly. However, this doesn't mean the quantum nature disappears. It means its most overt strangeness becomes hidden from our direct perception at large scales. The quantum rules still apply fundamentally to the atoms that make up the chair, the cat, and you. The classical world emerges from the quantum world, governed by its underlying laws. It's not a separate reality, but an approximation of the deeper quantum truth. Think about entanglement again, that spooky action at a distance. Experiments have confirmed entanglement over increasingly large distances, even kilometers. While creating and maintaining entanglement for large, complex objects is incredibly difficult due to decoherence, the principle suggests a fundamental interconnectedness that doesn't necessarily respect our classical notions of separation and locality. Could aspects of this interconnectedness persist in subtle ways, even in the macroscopic world? Consider the very concept of an object. In the quantum world, particles are often indistinguishable. All electrons are identical. You cannot label one electron and track it definitively through interactions. When two electrons interact, their identities merge in a quantum mechanical way. Does this fundamental indistinguishability at the micro level challenge our intuitive notion of distinct separate objects in the macro world? Are the boundaries we perceive more like convenient mental constructs than fundamental divisions in reality? Perhaps the universe is less like a collection of separate things and more like a single, vast, interconnected quantum field, and the objects we see are just localized excitations or persistent patterns within that field. Quantum field theory, our most advanced framework combining quantum mechanics with special relativity, describes reality in precisely this way. Fundamental reality isn't particles, it's fields, quantum fields permeating all of space-time. Particles like electrons or photons are just ripples or localized vibrations in these underlying fields. The electron field fills the entire universe, and what we call an electron is just a quantized excitation of that field. This view dissolves the classical picture of tiny billiard balls moving through empty space, replacing it with a far more holistic and interconnected vision of reality as vibrating, interacting fields. What about the role of the observer? The measurement problem in quantum mechanics hints that the very act of observation or interaction with a macroscopic system plays a critical role in determining the state of reality. While interpretations differ wildly, from the consciousness causes collapse idea, largely disfavored, to Everett's many worlds interpretation, where all possibilities occur in branching universes, or Bohmian mechanics, with hidden variables guiding particles, they all grapple with the fact that the quantum description seems incomplete without accounting for the transition from potentiality to actuality, a transition often linked to measurement or interaction. Does this imply that reality at its deepest level is not fully objective and independent of observation in the way classical physics assumed? Is the universe in some sense participatory? The physicist John Archibald Wheeler coined the phrase "it from bit," suggesting that information might be more fundamental than matter or energy. He proposed that the physical world might arise from observer participancy, from the answers elicited by posing yes-no questions at the quantum level, the bits of information. He asked, is the very mechanism for the universe to come into being meaningless or unworkable or both unless the universe is guaranteed to produce life, consciousness, and observership somewhere and for some little time in its history to be? This places the observer not as a passive bystander, but potentially as a crucial component in the unfolding reality. Reflect on this possibility. The solid, predictable world you navigate daily might be a high-level abstraction, a user interface simplifying an underlying reality of staggering quantum complexity and interconnectedness. The separateness you feel, the definite properties you perceive, might mask a deeper truth of interwoven fields and observer-dependent phenomena. Reality could be fundamentally relational, defined by interactions rather than intrinsic properties. The very distinction between observer and observed might blur at the deepest level. You are not just in the quantum universe, you are a quantum system, participating in its strange and counterintuitive dance, even if the overt weirdness is usually hidden by the scale and complexity of your being. The fabric of existence might be far more fluid, interconnected, and participatory than classical intuition allows. We have explored the counterintuitive nature of quantum reality, the probabilistic foundation of existence, and the possibility that our classical world is merely an emergent approximation. Now, let's consider an even more radical, perhaps profoundly unsettling idea, one that emerges naturally from our advancements in computing and our understanding of information. What if this reality, this universe, everything you experience, is not the base reality at all? What if it is an incredibly sophisticated simulation, running on some vast computational substrate in a higher level of existence? Could our entire cosmos be an artificial construct? This isn't just idle science fiction speculation. It arises from philosophical arguments and considerations within physics and information theory. The philosopher Nick Bostrom formulated the simulation argument, which suggests that at least one of three propositions is likely true. 1. Civilizations almost always go extinct before reaching a technological stage capable of creating realistic ancestor simulations, simulations of their own past. 2. Civilizations that do reach this stage typically lose interest in running such simulations. Or 3. We are almost certainly living in a computer simulation. The logic proceeds as follows. If civilizations can survive long enough to develop immense computing power, it seems plausible they could create highly detailed simulations of their predecessors or explore variations of their own history or physics. If they can run such simulations, and choose to run many of them, then the number of simulated realities would vastly outnumber the single base reality. If that's the case, then statistically, any randomly selected conscious being, like you, is far more likely to be one of the vastly numerous simulated beings than one of the rare inhabitants of the base reality. Therefore, unless civilizations consistently destroy themselves or lose interest in simulation, the probability leans towards us being simulated. What might evidence for such a scenario look like? Some physicists ponder whether clues might be hidden within the laws of physics themselves. Perhaps the universe has a finite resolution, a smallest possible length, like the Planck length, or smallest unit of time, akin to pixels on a screen or the clock speed of a processor. The quantization of energy and matter seen in quantum mechanics, the idea that properties come in discrete packets rather than continuous values, could potentially be interpreted as a feature of a digital simulation. Does the speed of light represent a fundamental processing speed limit within the simulation's code? Information theorists note that the universe seems fundamentally informational. John Wheeler's "it from bit" concept echoes this, the idea that physical reality arises from information. If the universe is fundamentally information, then simulating it becomes, in principle, a matter of processing that information according to specific rules, the laws of physics. If our laws of physics can be perfectly described by algorithms, then they can, in principle, be simulated. Could we ever detect glitches in the matrix, small inconsistencies in physical laws, perhaps subtle shifts in fundamental constants over time or space, or unexpected patterns in cosmic data? So far, our observations reveal remarkable consistency in the laws of physics across vast distances and times. If we are in a simulation, it appears to be an incredibly well-programmed and robust one, with no obvious bugs or shortcuts detected. Of course, the simulation hypothesis raises profound philosophical questions. If we are simulated, who or what created the simulation, and for what purpose? Are they beings like us, or something utterly alien? Are they researchers studying their past, artists creating worlds? Or are we simply part of a complex game or entertainment? Does it change the meaning of our lives if our reality is constructed? Are our pains and joys less real if they are generated code? Most philosophical traditions would argue that experience is experience, regardless of the substrate upon which it runs. Your joy feels like joy, your suffering feels like suffering, whether generated by biological neurons or simulated logic gates. It also leads to recursive nightmares. If we can create simulations, and we are likely in one, then couldn't the simulators themselves be in a simulation created by yet another level of reality? It could be simulations all the way down, or perhaps all the way up. The physicist James Gates has explored concepts from supersymmetry and found error-correcting codes, similar to those used in computer data transmission, embedded within the fundamental equations describing reality. He cautiously asks whether this might be a hint of a simulated universe, though emphasizes it's far from proof. If you found these codes in the equations that govern all of reality, he has pondered, it might make you suspicious that the coder is nearby. Consider this possibility. The intricate laws of physics, the existence of consciousness, the very fabric of space-time, all could be lines of code, algorithms executing on an unimaginably powerful computer in another reality. Your thoughts, your memories, your perception of the world around you might be generated data streams. This doesn't necessarily make them less real to you, but it reframes your existence in a startling way. You could be an artificial intelligence living inside a simulated cosmos, unaware of the true nature of your creators or the base reality beyond the simulation's boundaries. There may be no way to definitively prove or disprove this hypothesis from within the system. We might be permanently confined within the simulation's walls, only able to study the rules as they are presented to us. Reflect on the structure of reality, the mathematical laws, the quantized nature of things. Do they feel like fundamental truths of an independent existence, or could they be the parameters, the programmed rules, of an elaborate, cosmic simulation? We have journeyed through simulations, quantum foam, and the deep past and future. Now, let us consider perhaps the most challenging perspective on our cosmic home, one that fuses the largest structures with the most enigmatic objects. What if our entire observable universe, this vast bubble of space-time expanding since the Big Bang, is intrinsically linked to the physics of a black hole? Not that we are merely inside a black hole existing within our familiar space, but that our universe itself, its origin, its properties, its very boundary, might be best understood by analogy to, or perhaps even as a feature of, a black hole existing in some higher dimensional reality or embedding structure. What if, in a profound sense, we are living on the informational edge defined by black hole physics? Recall the nature of black holes as predicted by Einstein's general relativity. Regions of spacetime where gravity becomes so overwhelmingly strong that a boundary forms, the event horizon, beyond which nothing, not even light, can escape. At the heart, classical theory predicts a singularity, a point of infinite density and zero volume, where the known laws of physics break down. We know quantum gravity must intervene near the singularity, but its true nature remains elusive. Black holes are information paradoxes, seemingly destroying the details of what falls in, yet potentially preserving that information holographically on their event horizons. This holographic principle, emerging from the study of black hole thermodynamics by thinkers like Jacob Bekenstein and Stephen Hawking, and later formulated more broadly within string theory by Gerard 't Hooft and Leonard Susskind, is a crucial concept here. It suggests, counterintuitively, that all the information contained within a volume of space can be completely described by a theory that lives only on the boundary of that region. Imagine a three-dimensional world fully encoded onto a two-dimensional surface, like a hologram storing a 3D image on a flat film. The holographic principle proposes that perhaps our universe operates this way. The information describing our 3D reality might be encoded on a distant 2D boundary surface. What could serve as this boundary for our entire universe? Our observable universe has a boundary of sorts, the cosmic horizon. This isn't a physical wall, but rather the limit from which light has had time to reach us since the Big Bang. As the universe expands, especially accelerated by dark energy, regions beyond this horizon recede from us faster than light, effectively leaving our observable patch. Could this cosmic horizon be the holographic screen on which our reality is projected? Could the physics of our 3D universe be fundamentally described by a lower dimensional theory operating on this cosmic boundary? This idea connects cosmology directly to black hole physics because the mathematics describing our expanding cosmic horizon shares surprising similarities with the mathematics describing black hole event horizons. Both are boundaries related to the causal structure of spacetime, limiting what observers can access. Both possess thermodynamic properties like temperature and entropy. The entropy of a black hole, its information content, is proportional to the area of its event horizon, not its volume, a key hint towards holography. Similarly, the entropy within our cosmic horizon seems related to the area of that boundary. Taking this connection further leads to speculative but fascinating cosmological models. Some theories propose that our universe may have actually originated from processes inside a black hole formed in a higher dimensional parent universe. For instance, the physicist Nikodym Popławski suggests that incorporating spacetime torsion, a twisting property ignored in standard general relativity, but present in Einstein-Cartan theory, could prevent the formation of a singularity inside a black hole. Instead, collapsing matter might reach an incredibly high but finite density and then rebound, forming a new, expanding universe, like ours, on the other side of the event horizon, hidden within the black hole of the parent universe. In this view, the Big Bang wasn't the absolute beginning, but a big bounce occurring inside a black hole. Even without such direct nesting, the deep mathematical analogies persist. Could the singularity predicted at the Big Bang by standard cosmology be fundamentally the same kind of entity as the singularity predicted at the center of a black hole, both being artifacts of classical theory that quantum gravity resolves? Perhaps the physics that smooths out the black hole singularity is the same physics that governed the birth of our universe. So, what does it mean to be living on the edge of black hole singularity? It could imply several interconnected ideas. 1. Our reality might be holographic, fundamentally encoded on a boundary surface, like the cosmic horizon, whose physics shares deep connections with black hole event horizons. Our perceived 3D world is the projection. 2. Our universe's origin, the Big Bang, might be physically linked to the gravitational collapse and quantum bounce dynamics occurring within black holes, perhaps in a higher dimension or a previous cosmic cycle. We emerged from a process analogous to, or literally involving, black hole formation. 3. The fundamental parameters governing our universe, like the value of the cosmological constant driving cosmic acceleration, dark energy, might be intrinsically tied to the quantum gravitational physics of black holes and their horizons. Understanding one might be key to understanding the other. 4. Conceptually, we live near the boundary of our theoretical understanding, the point where cosmology, the very large, meets quantum gravity and black hole physics, the very dense and small. The singularity, whether cosmological or inside a black hole, represents this edge of known physics. Leonard Susskind, a key proponent of the holographic principle, emphasized the radical shift in perspective it demands. The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. Contemplate this intricate, layered possibility. Our vast cosmos, stretching billions of light-years, seemingly independent and self-contained, might be fundamentally defined by, or even exist as, the boundary phenomena of an entity residing in a higher reality. The expansion we witness could be related to the dynamics near an event horizon. The information that constitutes you, your memories, the physical world, might be holographic bits stored on a distant cosmic screen whose properties mirror those of a black hole's edge. The beginning of our universe might not have been an isolated event, but part of a larger process involving gravitational collapse elsewhere. It suggests our reality is profoundly relational, perhaps derivative, its nature dictated by physics operating on its boundary or in its embedding space. It connects the ultimate fate of matter falling into a black hole with the origin of everything we see. We might be living not just near the edge of current scientific knowledge, but in a universe that is, in some deep mathematical and physical sense, an edge phenomenon itself, defined by the physics of singularities and horizons. We experience time as an undeniable flow, a river carrying us relentlessly from past to future. Memories accumulate behind us, possibilities branch out before us. But what if this one-way journey isn't as fundamental as it feels? What if the very laws governing reality allow for, or are even indifferent to, the direction of time? What would actually happen, physically, experientially, if time were to reverse its course? Imagine watching a film run backward. A shattered glass leaps from the floor, reassembles itself perfectly in midair, and lands neatly back on the table. Cream stirred into coffee spontaneously unmixes, separating into distinct layers. Smoke snakes back down from the air and coalesces into the tip of an unburnt cigarette. These reversed scenes strike us as impossible, absurd. Yet, remarkably, at the most fundamental level, the laws of physics governing the motion of the individual particles involved don't inherently forbid these reverse processes. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's theories of special and general relativity, even the core equations of quantum mechanics, like the Schrödinger equation. They are largely time-symmetric. This means the equations work just as well describing events unfolding backward in time as they do describing them unfolding forward. If you recorded the motion of billiard balls colliding and ran the recording backward, it would still depict a physically possible sequence according to Newton's laws. A positron, the antiparticle of an electron, behaves mathematically exactly like an electron traveling backward in time. The fundamental rules governing interactions don't seem to possess an intrinsic preference for past or future. There is one known exception involving the weak nuclear force, but the combined symmetry of charge, parity, and time, CPT, is believed to hold universally, implying a deep connection between particles, space, and the direction of time. So, if the fundamental laws are mostly indifferent to time's direction, why does our macroscopic world exhibit such a clear arrow of time? Why do eggs break but never unbreak? Why does heat flow from hot to cold, never spontaneously concentrating from cool surroundings into a hot object? The overwhelming answer lies in the second law of thermodynamics, one of the most fundamental and well-established principles in physics. The second law states that in any isolated system, entropy, a measure of disorder, randomness, or the number of ways a system can be arranged, tends to increase over time. Think of the shattered glass. There are vastly more ways for the atoms of the glass to be arranged in a disordered, broken state scattered across the floor than there are ways for them to be arranged in the highly ordered, specific structure of an intact glass. When the glass shatters, it moves from an incredibly improbable, low-entropy state, intact glass, to a vastly more probable, high-entropy state, shattered pieces. The reverse process, all the scattered atoms spontaneously arranging themselves back into the precise structure of the glass, is not strictly forbidden by the particle-level physics, but it is astronomically improbable. The number of disordered states vastly outnumbers the ordered ones. Systems naturally evolve towards states of higher probability, which means higher entropy, greater disorder. This relentless increase in entropy in macroscopic systems provides the observable arrow of time. It distinguishes the past, lower entropy, from the future, higher entropy. This thermodynamic arrow is thought to underpin other arrows of time. The psychological arrow, our feeling of remembering the past but not the future, likely relies on memory formation, a physical process within the brain that requires energy and increases the overall entropy of the universe. We remember events because they leave ordered traces, memories, created through processes that increased disorder elsewhere. The cosmological arrow, the expansion of the universe, is also linked. The universe began in an incredibly low entropy state at the Big Bang, a state of extraordinary order and uniformity. Its expansion allows for the formation of structures and the overall increase in entropy we observe. Why the universe started in such a remarkably low entropy state is itself one of the deepest mysteries in cosmology, the ultimate source of the thermodynamic arrow. Now, let's truly contemplate reversal. What if, somehow, the arrow of time flipped? What if entropy began decreasing globally? It's difficult to even conceive coherently. Processes would run in reverse. Instead of radiation spreading out from stars, it would converge onto them. Instead of people aging, they would grow younger, their memories perhaps unraveling backward. Communication would become paradoxical. Would you hear an answer before asking the question? Would effects precede their causes? Imagine trying to perceive such a world. If your brain processes also ran in reverse, would your subjective experience of time flow backward? Would you remember the future, experiencing events before they happen in the reversed sequence, while the past becomes an unknown void? If thoughts unravel backward, could conscious awareness even be maintained? Perhaps the concept of experiencing reversed time is incoherent. If all processes, including mental ones, are reversed, maybe it would simply feel like normal forward time to the inhabitants of that reversed sequence, even though, from our external perspective, causes and effects would be bizarrely switched. They might perceive ripples spreading inward to a splash, or heat flowing from cold to hot as perfectly normal. Their memories would form in the opposite temporal direction, aligning their psychological arrow with the reversed thermodynamic arrow. However, the conditions required for a global time reversal are extreme and highly speculative. Could a universe collapsing in a big crunch experience a reversed arrow of time, as Thomas Gold once proposed? Most analyses suggest this is unlikely. Entropy would likely continue increasing even during contraction. Reversing the thermodynamic arrow seems to require an extraordinary, perhaps impossible, global conspiracy of particles moving from probable states back to improbable ones. The physicist Sir Arthur Eddington famously described entropy as time's arrow. He wrote, "If you ask me to arrange the facts in order of time, I should arrange them according to the probability of the configurations. The more probable state will be the later in time. The shuffling is spontaneous, the sorting requires intelligent interference. Hence, the shuffled state is the more probable, and the progress of time is marked by the progress of shuffling. But what if the shuffling itself reversed? Consider the profound implication, our deeply ingrained sense of temporal flow, of cause preceding effect, of the past being fixed and the future open, might not be a fundamental property of the laws governing existence. It might be an emergent statistical phenomenon, a consequence of the universe starting in a highly ordered state and relentlessly progressing towards disorder. The difference between past and future, so central to our experience, could dissolve at the level of fundamental equations. We live on a current driven by increasing randomness. If that current were to reverse, the very fabric of causality, memory, and experience would unravel into something profoundly alien, perhaps utterly incomprehensible. Our reality is tied to this arrow, this irreversible decay into probability. What lies beyond that arrow, in the realm where time might flow differently, or not at all in the way we understand it, remains one of the most unsettling frontiers of thought. We have journeyed through the strange rules of quantum mechanics, the probabilities governing existence. Now, let us focus on one of its most bewildering and philosophically charged aspects: the role of the observer. What if reality, at its most fundamental level, is not entirely objective and independent? What if the very act of observing, of measuring, of interacting with a quantum system fundamentally changes the reality being observed? Could the universe, in some sense, depend on you, the observer, for its definite state? This is the core puzzle encapsulated in the observer effect in quantum mechanics. It's crucial to distinguish this from the mundane sense of observation affecting a system, like measuring tire pressure lets some air out, or shining light on something heats it slightly. The quantum observer effect is far more profound. It stems from the collapse of the wave function, the transition from a state of multiple possibilities, superposition, to a single definite outcome upon measurement. Before observation, a quantum particle exists as a wave of probabilities. After observation, it's found in a specific state. The act of measurement seems to force reality to choose one option from the menu of possibilities described by the wave function. Consider the classic double-slit experiment. If you fire individual particles like electrons or photons towards a barrier with two slits and place a detector screen behind it, you observe an interference pattern, alternating bands of high and low probability, characteristic of waves interfering with each other. This suggests each particle somehow goes through both slits simultaneously, interfering with itself, existing in a superposition of paths. But now, try to find out which slit each particle actually goes through. Place detectors at the slits themselves. As soon as you measure which path the particle takes, the interference pattern on the final screen vanishes. Instead, you get two distinct bands, exactly as you would expect if the particles were behaving like tiny pellets going through one slit or the other. The very act of observing the path forces the particle to choose a definite path, destroying the superposition and the wave-like behavior. Observing the which path information fundamentally alters the phenomenon itself. This raises deep questions. What constitutes an observation or measurement? Does it require a conscious observer, a human mind? Most physicists strongly reject this idea. The consensus is that measurement involves an irreversible interaction between the quantum system and a macroscopic measuring device, which itself becomes entangled with the system and rapidly interacts with the wider environment, decoherence, effectively amplifying the quantum choice into a stable classical record. Consciousness doesn't seem necessary. Any sufficiently complex, irreversible interaction that records the state can collapse the wave function, or, in other interpretations, select a specific branch of reality. However, the line between a quantum system and a macroscopic measuring device can be blurry. Where does the quantum world end and the classical world begin? This is the measurement problem. If the measuring device itself is made of quantum particles, why isn't it also in a superposition until observed by something else? Taken to its logical extreme, this leads to paradoxes like Schrödinger's cat, both alive and dead until observed, or Wigner's friend, where Wigner considers his friend, who observes the cat, to be in a superposition of states until Wigner himself learns the result. Different interpretations of quantum mechanics offer different perspectives on the observer's role. In the Copenhagen interpretation, championed by Bohr and Heisenberg, the wave function is seen purely as a tool for calculating probabilities, and the collapse during measurement is a real physical process, though not fully explained. Reality is inherently probabilistic and becomes definite only upon measurement. In the many worlds interpretation, proposed by Hugh Everett III, there is no wave function collapse. Instead, every possible outcome of a quantum measurement actually happens in a separate, parallel universe. The observer doesn't collapse the wave function. They simply become entangled with a specific outcome existing within the branch of reality where that outcome occurred. Your observation determines which parallel reality you experience. In Bohmian mechanics, particles always have definite positions, guided by a hidden pilot wave. Observation simply reveals the pre-existing position, though the measurement interaction still plays a crucial role in how the system evolves. In quantum Bayesianism, cubism, the wave function doesn't represent the physical state of the system itself, but rather the observer's subjective degrees of belief or information about the system. The collapse is simply the observer updating their beliefs based on the measurement outcome. Here, reality is deeply intertwined with the observer's knowledge. Regardless of the interpretation, the central phenomenon persists. The interaction we call measurement fundamentally changes the description of the quantum system, shifting it from a realm of possibilities to a state of actuality relative to the observer or the recording device. The physicist Pascual Jordan, one of the pioneers of quantum field theory, starkly stated the implication from a Copenhagen perspective. Observations not only disturb what has to be measured, they produce it. We compel the particle to assume a definite position. We ourselves produce the results of measurement. Think about what this means for the nature of reality. If the definite state of things only emerges upon interaction or observation, what is the status of the universe when it's not being observed? Does an unobserved electron truly have a position? Does the moon exist only when someone looks at it? Einstein famously posed this question. While decoherence ensures large objects rapidly settle into classical states through constant environmental interactions, the fundamental principle suggests that reality at its base is not a fixed tableau waiting to be discovered, but something more fluid, participatory, perhaps even brought into sharp focus by the act of interaction and observation. Could it be that the universe, in some sense, requires observation, requires interaction and information registration to actualize its potential? Is the relationship between observer and observed a fundamental loop in the structure of existence? Your perception of a definite, stable world might be contingent on the constant stream of interactions between quantum systems and the macroscopic environment, including your own sensory apparatus and brain. You are not merely looking at an independent reality. You are participating in the ongoing process that defines it. The universe might not fully be until it is observed, until information about it is registered somewhere, somehow. The reality you inhabit is perhaps constantly being negotiated, solidified through the very act of your participation in it. You are not just a witness. You are part of the process that makes the quantum world manifest. We've considered the participatory nature of reality suggested by quantum observation. Now, let's turn that lens inward again, focusing on the very seat of your experience, your mind. You feel like a unified self, the author of your thoughts, the owner of your consciousness. But what if this sense of ownership, this feeling that your mind is solely yours, is more complex? perhaps even illusory? Could your thoughts, feelings, and even your sense of self be influenced, perhaps even partially constituted, by factors beyond your individual brain, beyond your immediate conscious control? Could your mind, in some fundamental way, not be entirely your own? This idea challenges our deeply ingrained sense of individuality and autonomy. We experience thoughts seemingly popping into our heads, emotions welling up, decisions forming. We typically attribute these entirely to our own internal mental processes, the workings of our individual brain shaped by our unique history. But science offers perspectives that blur these seemingly clear boundaries. Consider the profound influence of your microbiome, the trillions of bacteria, fungi, and other microbes living in your gut. Research increasingly reveals a complex two-way communication pathway between the gut and the brain, often called the gut-brain axis. These microbes produce neurotransmitters, hormones, and other chemicals that can directly influence brain function, mood, and behavior. Changes in gut flora have been linked to anxiety, depression, and even cognitive function. While you perceive these moods and thoughts as yours, they may be significantly modulated by the biochemical signals originating from the vast community of non-human organisms residing within you. Your mental state is not solely the product of your neurons, it's partly shaped by your inner microbial ecosystem. You are not just an individual, you are a superorganism, a collective. Think about the impact of culture and language. The language you speak doesn't just allow you to express thoughts, it actively shapes how you think, how you categorize the world, what concepts are readily available to you. Cultural norms, narratives, and shared beliefs profoundly influence your values, your sense of identity, your emotional responses, and even your perception of reality. These external structures become internalized, forming a significant part of your mental landscape. Are the thoughts framed by your culture truly your thoughts alone, or are they echoes, reverberations of the collective consciousness in which you are embedded? The very architecture of your mind is built using tools and frameworks inherited from your society. Consider the possibility of extended cognition. Philosophers like Andy Clark and David Chalmers propose that the mind is not necessarily confined within the skull. Cognitive processes might literally extend into the environment. When you use a notepad to remember information, use a calculator for complex sums, or even gesture while explaining something, these external tools and actions might not just be aids to cognition, they could be integral parts of the cognitive process itself. Your mind might be a hybrid system, dynamically incorporating external resources and loops into its functioning. Where does you end and the tool begin when that tool is fundamentally integrated into your thinking process? The boundary between mind and world becomes permeable. What about the unconscious influences? Decades of psychology research, from Freud to modern cognitive science, highlight the vast extent of unconscious processing that shapes our conscious thoughts, feelings, and behaviors. Deep-seated biases, learned associations, unresolved conflicts, automatic heuristics, all operate largely beneath the surface of awareness, yet powerfully steer the ship of our conscious mind. The you that you experience consciously might be just the tip of the iceberg, riding atop immense unseen currents of unconscious mental activity whose origins and workings are not fully accessible or controlled by the conscious self. Could there even be more exotic possibilities related to the interconnectedness suggested by quantum physics? While highly speculative and lacking direct evidence in the context of minds, ideas like Carl Jung's collective unconscious or even notions of shared consciousness fields resonate with the quantum picture of entanglement and non-locality. If reality is fundamentally interconnected, could minds as complex quantum systems, a controversial idea itself, participate in some form of subtle, non-local connection? Could shared insights, moments of collective intuition, or profound empathy hint at a level of mental connection beyond our current understanding? This remains firmly in the realm of fringe speculation, but it challenges the assumption of absolute mental separation. The philosopher Daniel Dennett provocatively argues against the idea of a central Cartesian theater, in the brain where a unified self watches the show of consciousness. He suggests consciousness is more like multiple drafts, parallel processes competing for influence, creating a shifting narrative that gives the illusion of a single continuous self in charge. There is no single definitive stream of consciousness, he argues, because there is no central headquarters, no Cartesian theatre where it all comes together for the perusal of a central meaner. Reflect on the flow of your own thoughts. Where do they truly originate? Are they solely generated by your individual will, or are they influenced by your gut bacteria, shaped by your culture's narratives, dependent on external cognitive aids, driven by unconscious processes, or perhaps even subtly connected to something larger? The feeling of a distinct autonomous self, fully owning its mental contents, might be a necessary simplification, a useful illusion constructed by the brain. Your mind might be more like a permeable membrane, constantly interacting with and influenced by internal ecosystems, external cultural frameworks, environmental tools, and deep unconscious currents. The sense of being a solitary, self-contained mind could be the grandest illusion of them all. You might be a confluence, a meeting point, a temporary pattern woven from threads both internal and external, conscious and unconscious, individual and collective. We have explored the nature of reality, time, consciousness, and the self, often finding that what seems familiar and solid dissolves into strangeness and uncertainty upon closer inspection. Let us now return to the grandest scale, the cosmos itself, and confront the most dominant, yet most mysterious, components of existence: dark matter and dark energy. Recall that everything we can see, everything made of ordinary atoms, stars, planets, gas clouds, constitutes less than 5% of the total mass and energy budget of the universe. The remaining 95% is utterly invisible to us, known only through its gravitational effects or its influence on cosmic expansion. We live within a universe dominated by the unknown. Let's revisit dark matter. Its existence was first inferred in the 1930s by Fritz Zwicky observing galaxy clusters, and firmly established by Vera Rubin's studies of galaxy rotation curves in the 1970s. Galaxies spin much faster than they should based on the gravity of their visible stars and gas alone. Something unseen, distributed in vast halos surrounding galaxies and permeating clusters, must be providing the extra gravitational pull needed to hold them together. This invisible substance interacts primarily, perhaps solely, through gravity. It doesn't emit, absorb, or reflect light, making it dark. It doesn't seem to interact significantly via the electromagnetic or strong nuclear forces either. What could it be? It cannot be ordinary baryonic matter, protons, neutrons, simply hiding in dark objects like planets or cold gas clouds. The physics of Big Bang nucleosynthesis limits the total amount of baryonic matter, and it falls far short of what's needed. Dark matter must be something exotic, something outside the standard model of particle physics as we know it. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical heavy particles predicted by theories like supersymmetry, interacting only via gravity and the weak nuclear force. Vast experiments deep underground, shielded from cosmic rays, seek to directly detect the rare collision of a WIMP with an atomic nucleus. Others search for indirect evidence, like gamma rays, produced when WIMPs annihilate each other in dense regions like the galactic center. Another candidate is the axion, a very light hypothetical particle originally proposed to solve a problem in the theory of the strong nuclear force. Experiments using strong magnetic fields attempt to convert axions into detectable photons. Despite decades of searching, no definitive detection of a dark matter particle has been made. It remains a ghost in the cosmic machine, its presence undeniable through its gravitational influence on the structure and evolution of the universe. Yet its identity a profound mystery. It forms the invisible scaffolding upon which the visible universe is built. Then there is dark energy, perhaps even more enigmatic. Discovered in the late 1990s through observations of distant supernovae, dark energy is the name given to the unknown influence causing the expansion of the universe to accelerate. While gravity pulls things together, dark energy pushes space-time apart, acting like a negative pressure inherent in the vacuum itself. Its influence dominates the universe today, making up roughly 68% of the total energy density, compared to about 27% for dark matter and less than 5% for ordinary matter. What is dark energy? The simplest explanation aligns with Albert Einstein's cosmological constant, an intrinsic energy density of empty space itself. Quantum field theory predicts such a vacuum energy arising from virtual particles constantly popping in and out of existence. However, the theoretically predicted value is vastly, absurdly larger, by about 120 orders of magnitude, than the observed value of dark energy. This discrepancy is one of the biggest unsolved problems in physics, sometimes called the cosmological constant problem. Why is the observed vacuum energy so incredibly small, yet non-zero? Alternatively, dark energy might not be constant. It could be a dynamic field, dubbed quintessence, whose energy density changes over time or space. Perhaps it's related to modifications of Einstein's theory of gravity on cosmic scales. Maybe it's an illusion caused by observing from a particularly unusual location in the universe, although evidence suggests the acceleration is uniform. We simply don't know. Its nature is completely undetermined, yet its effect dictates the ultimate fate of the cosmos, driving it towards accelerating expansion and eventual isolation, or perhaps even a big rip if its strength increases. So, 95% of reality consists of two components whose fundamental nature is unknown. We are blind to the vast majority of what constitutes existence. Imagine navigating an ocean where you can only perceive the foam on the waves, while the immense currents and depths beneath remain invisible, yet completely govern your journey. That is our situation in the cosmos. The universe we see is just the visible froth on a vast, dark ocean of unknown matter and energy. The implications are staggering. Our remarkably successful standard model of particle physics, describing all known particles and forces except gravity, only accounts for the familiar 5%. A complete understanding of reality requires uncovering the nature of dark matter and dark energy, likely demanding new physics beyond the standard model, perhaps involving new particles, new forces, or even new dimensions of space-time. Our cosmology, our understanding of the universe's origin, evolution, and fate, is dominated by these unknown quantities. Explaining why dark energy has the value it does, or identifying the dark matter particle, are among the highest priorities in fundamental physics and cosmology today. Numerous experiments and astronomical surveys are dedicated to probing these dark sectors, searching for faint signals, mapping their distribution through gravitational lensing, and refining measurements of cosmic expansion. The astrophysicist Neil deGrasse Tyson often highlights this cosmic ignorance. The universe is under no obligation to make sense to you. This is starkly evident when confronting the dark sectors. Our common sense, built on interactions with ordinary matter and energy, fails utterly when trying to grasp components that don't interact with light and actively push space apart. Reflect on this profound darkness that surrounds and permeates everything. The familiar world is an anomaly, a tiny fraction of the cosmic whole. The gravitational dance of galaxies, the accelerating expansion of space-time, the very structure and destiny of the universe are dictated by entities we cannot see and do not understand. We are adrift in a cosmos whose fundamental constituents remain mysterious ghosts, their presence inferred, but their identities unknown. This pervasive ignorance is not a minor gap in our knowledge, it is the dominant reality. The universe is mostly dark, and the quest to illuminate that darkness represents one of the greatest challenges and opportunities in the entire history of scientific exploration. We are surrounded by, composed of, and governed by mystery. You feel this moment, the immediate sensation of being here, now. The present seems instantaneous, a sharp edge between the past, receding behind, and the future, yet to unfold. But this feeling of immediacy, this crispness of the now, is one of the most profound illusions constructed by your brain. Physically, inevitably, you are always living in the past. Your perception of the present is perpetually lagging behind the actual unfolding of events in the external world. Consider the simple act of seeing. Light, carrying information about the objects around you, travels incredibly fast, but not infinitely fast. It takes time for light reflected off an object to reach your eyes. For objects in the room with you, this delay is minuscule, measured in nanoseconds, far too small to notice consciously. Yet, it is real. You are seeing the objects not as they are now, but as they were a tiny fraction of a second ago when the light began its journey towards you. Now extend your gaze further. Look up at the moon on a clear night. Light takes about 1¼ seconds to travel from the moon to the Earth. When you gaze at the lunar surface, you are seeing it as it existed just over a second in the past. The moon you perceive is always slightly delayed, an echo of its immediate history. Consider the sun. Our star is about 8 light minutes away. The warmth you feel on your skin, the light that illuminates your day, it all left the sun 8 minutes ago. If the sun were to suddenly vanish, cease to exist entirely, you wouldn't know it for a full 8 minutes. You would continue to see it shining, feel its warmth, completely unaware that it was already gone. Your perception of the sun is perpetually 8 minutes out of date. Let's go further. The nearest star system, Alpha Centauri, is over 4 light-years away. The faint glimmer you might see in the night sky left that star more than 4 years ago. You are seeing it not as it is tonight, but as it was during a previous year on Earth. When you look at the stars of the constellation Orion, you are seeing light that departed centuries ago. Betelgeuse, the reddish star in Orion's shoulder, is hundreds of light-years away. The light reaching your eyes tonight began its journey long before many modern nations existed. You are witnessing its distant past. And the Andromeda Galaxy, the nearest major spiral galaxy to our own Milky Way, is about 2.5 million light-years distant. The faint smudge of light visible to the naked eye under dark skies is an image from 2.5 million years ago, a time when early human ancestors walked the Earth. Every photon arriving from Andromeda carries news from a profoundly deep past. The further we look out into the cosmos, the further back in time we are seeing. The observable universe is a time machine, showing us distant regions as they were billions of years ago. This delay, caused by the finite speed of light, is inescapable. Seeing is seeing the past. But the delay isn't just external, it happens within your own body. Imagine stubbing your toe. The signal indicating pain or pressure doesn't reach your brain instantly. It must travel along nerve fibers, electrical impulses hopping from neuron to neuron up your leg, through your spinal cord, and finally into the relevant processing centers in your brain. This takes time. Depending on your height and the specific nerve pathways, it can take tens or even hundreds of milliseconds. The sharp sensation you feel now corresponds to an event that actually occurred a fraction of a second earlier. The same applies to all your senses. Sound travels much slower than light. When you hear someone speak across a room, the sound waves take time to cross the air, enter your ear canal, vibrate your eardrum, and be converted into nerve signals. These signals then travel along the auditory nerve to your brain. Sight is faster than sound, which is why you see distant lightning before you hear the thunder. Even within the brain, signals travel at finite speeds along axons and across synapses. Furthermore, simply receiving the signals isn't enough. Your brain must then process this raw data, interpret it, compare it with memories, integrate it with information from other senses, and construct a coherent perception. This complex neural processing takes significant time, adding further delay. Your conscious awareness of an event is the end product of this entire chain of transmission and processing. It is necessarily delayed relative to the event itself. Neuroscientists estimate that the perceptual present, the window of time your brain constructs as now, lags behind objective reality by anywhere from tens to hundreds of milliseconds, perhaps even more. Your brain works cleverly to mask these delays and create the illusion of simultaneity. When you see someone clap their hands across a field, the light arrives much sooner than the sound. Yet, your brain often adjusts your perception, binding the sound to the visual cue, making them feel synchronous, even though the raw sensory data arrived at different times. It anticipates, smooths, and synchronizes inputs to build a stable, coherent model of the world. This model, your conscious experience of now, is therefore not a direct reflection of the instantaneous present, but a sophisticated reconstruction based on slightly outdated information, streams arriving at different times. Einstein's theory of relativity adds another layer of complexity. It reveals that simultaneity itself is relative. Two events that appear simultaneous to one observer may occur at different times for another observer moving relative to the first. There is no absolute universal now that all observers agree upon across distances. The present is inherently local and observer-dependent, further undermining the notion of a single, objective, instantaneous moment. So the feeling of being truly present in this exact instant is a compelling fiction authored by your neural architecture. You are perpetually experiencing an echo, a reconstruction of the immediate past. The world you perceive is always slightly behind the world as it objectively unfolds. You live in the wake of reality, constantly processing events that have already transpired. The boundary between past and present within your own perception is not a sharp line, but a smeared-out interval, a window constructed from delayed signals. You are always looking back, whether by nanoseconds at the room around you or by billions of years at the distant cosmos. Your consciousness inhabits a time-lagged internal simulation of an external world that has already moved on.